For STM, we implemented the following. Firstly, encoders which calculates the distance travelled to determine when to stop, X and Y position of the robot, and PID for DC motor. Secondly, an instruction buffer to store instructions from RPI. Thirdly, gyroscope to find turning angle and determine when to stop at certain angle, and PID for servo motor. Finally, an IR sensor to prevent collision. Some special implementation that we did are: firstly, the algorithm prefers the robot to have a tight 90-degree turn. To achieve this, we implemented a 60-degree turn, followed by a backward movement, and then complete the remaining 30-degree turn. Next, we configured a PID controller for servo motor to adjust the robot if it deviates from its target angle. PID is also used for DC motor to ensure both wheels turn at the same time.
For our image rack model, we took images using iPhone and Pi camera from different angles and lighting conditions. With our dataset, we used RoboFlow to annotate and augment the images, obtaining a total of 10,000 images. We also trained a YOLO V5 model using the GPU on Google Colab and obtained a MDP of 0.98. Therefore, the model is capable of recognizing images under different conditions, including times when only half an image is captured.
Some problems encountered include our model's misrecognition of objects which are not part of the trained images. To circumvent this, we set the confidence threshold to be at least 0.8. In situations where two images are near to each other, we set the program to only return the front image, which has the bigger bounding box area.
So the first problem that we have is that our robot occasionally crashes into the obstacle. So to prevent this, we changed our implementation of the arena map from a 20 by 20 grid to a 40 by 40 grid. This 40 by 40 grid allows us to be able to pad each side of the obstacle by 15 units instead of 10. Hence, we are able to attain a lower collision rate.
Another limitation we have is the inconsistent robot movements. After many discussions with the STM team, we found that backward turn movements are prone to have more errors. To avoid this, we adjusted our algorithm such that it only utilizes straight backward movements to formulate the robot's path.
The Android application has four main functions: Bluetooth connectivity, two-way communication to the robot and the RPI, configuration of the arena, and control of the robot. The application uses Bluetooth to connect to the RPI, which in turn connects it to the robot. The Discover Devices button scans for all Bluetooth devices in the region, and the Connect button opens the connection to the RPI. Before running the robot, we use the Android application to plot the coordinates of the obstacles on the arena, including the faces of the obstacle. We also use this function to indicate the starting position of the robot. The drag function allows us to change the position of the obstacle, while the cross button allows us to remove the obstacle cells. Communication between the Android and other components are made easy via the Communication tab, where messages can be sent or received from the robot and RPI. The robot sends coordinates and directions via the communication channel, which is then updated live on the application. Once the camera recognizes the image on the obstacle, the image ID is sent via this communication channel as well and is updated on the arena on the faces of the obstacle. Lastly, the control button commands the robot to move up, down, left, and right. The Android application was coded in Java using Android Studio to create a minimal and simple-to-use application.
The RPI serves as the mean of communication between the other modules through the use of multiprocessing. We implemented a queue system where the commands to be sent to the STM are first stored in a separate queue from the main message queue. Only after the STM returns a message that has completed the previous instruction, then will the message be moved to the main queue to be queued up for sending. The rest of the commands are moved up and are ready to receive the next instruction. When the STM message queue empties out, the next incoming instruction completion message will begin the image recognition process and then generate an image ID. This image ID will then be sent to the algorithm as an OK signal for the algorithm to send us the next set of instructions required to navigate to the next obstacle.